Welcome, Chem 1. In Unit 6, we've talked about ions, ionic bonding, and compounds that form from ionic bonding. Today we're going to talk specifically about one of those compounds called a hydrate. It's when water gets trapped in ionic crystal. Let's get started. We've learned that ionically bonded substances are typically repeating patterns of cations and anions, and they typically make crystal structures. Well, often those crystal structures have gaps in them. If water gets trapped in those gaps between the cations and anions, we call that a hydrate. The way we write a hydrate is by putting the cation and anion, the ionic compound, and then drawing a dot, kind of like a multiplication symbol, and then showing how many water molecules are trapped in those ionic crystals. This gives us a ratio of ionic compound to water. If we would heat this hydrate up, the water would separate from the ionic compound, and we would get what we call an anhydrous salt. So the copper sulfate in this case is the anhydrous salt. A lot of times I think of the word anhydrous like dehydrated, like we are removing the water. Here's just a picture that's showing the cations and anions and how the water is trapped in between those cations and anions. And if we heated it up, it would separate into the ionic compound and the water. The naming of hydrates is pretty straightforward. We use a Greek prefix system that you're probably familiar with to tell how many water molecules are trapped inside the ionic compound. So mono is 1, di is 2, tri is 3, and tetra is 4. Goes all the way up to deca at 10. So if we were going to name these substances, the first thing we would do is just name the ionic compound. We know this is copper, and we know that copper has multiple oxidation states. So we're going to put a parentheses there. And we know that SO4 is sulfate. If you remember, sulfate is a -2 charge, which means this copper has to be a +2. So we would put copper 2. The next thing we do is use a prefix to tell how many water molecules are trapped inside this ionic compound. 5, the prefix is penta, so we would call this copper 2 sulfate pentahydrate. The next one, we have sodium carbonate, and there are 10 water molecules, so that would be decahydrate. And then finally we have nickel chloride. This would be nickel 2 chloride because each chloride's a -1. And the prefix for 7 is hepta. So this would be heptahydrate. So the naming is pretty straightforward. Another thing we want you to be able to do with hydrates, because we'll be doing it in lab, is to determine the percent composition. Let's review percent composition from back in Unit 2. Remember, whenever you want to find the percent comp of anything, a chemical, a bag of M&Ms, it's the part you're looking at over the whole times 100, and that will tell you the percent. And when we use chemicals, we're focusing on the mass. So if we wanted to find the percent composition of sodium oxide, the first thing we would want to do is add up the mass of all the atoms in that compound. So the subscript 2 tells us we have 2 sodium atoms, and the atomic mass of sodium is 23.0. With oxygen, we have the mass of 16.0, and there's only one of them. We multiply those out and add them together, and we get a total mass of 62.0. Now, we can put the mass of sodium over the total mass, and the mass of oxygen over the total mass, which is what's happening over here. And then we divide and multiply by 100, and we get our answers of 74.2 and 25.8%. This should be reviewed back from Unit 2. But now let's try something new and find the percent of water within this hydrate. The first thing I like to do is add up the mass of just the salt, which is 106.0. Then I need to add up the mass of the water, and I'm going to keep the water molecule together because that's what I want the percentage of. Then I take the mass of the water molecule and multiply it by 10 because this is decahydrate. A good molar mass to remember is water, which is 18.0. Now I'm going to add these two masses together to get my total mass, which is 286.0, and then I take the part that's water, 180, and divide by the total mass, and multiply by 100. This gives us a percentage of 62.9%. Really, all this is the mass of the water over the mass of the entire hydrate. With this example here, they want us to name the compound and then write the equation for it breaking apart after it's heated. We've already named this compound. It's copper 2 sulfate pentahydrate because there are 5 water molecules. The way you write a dehydration into anhydrous salt and water vapor is by first showing that they're together using this dot. The dot indicates that they are together and therefore a hydrate. And then after we add heat, they're going to split apart into the anhydrous salts and the 5 water molecules. The percent composition of this, we'd add up the mass of the salt. Here's 1 copper, 1 sulfur, and here are 4 oxygen atoms. And then we have 5 water molecules, which is a mass of 90. We add them all up to get 249.7. We put the mass of the water, which is 90, over the total mass and multiply by 100. And we can see that this hydrate has 36% water by mass. If you need more examples, we can work through those in class together. The next thing we're going to talk about is metallic bonding. We don't spend a lot of time on metallic bonding in this course, but it does involve cations, which is why we kind of put it with ionic bond. Metallic bonds happen between metals and metals. Metals want to lose electrons. Metal cations will become very close together and their electrons will disassociate. This allows electrons to travel freely in between multiple different metallic cations. A lot of times we call these delocalized electrons, or we call it a sea of electrons, because the electrons are free to move within the metallic body. This sea of electrons is considered mobile and flexible and allows for electron movement. So it's similar to an ionic bond in that we have metallic cations, but we also have these negative particles, these electrons that are traveling throughout, which is what makes the metal cation lattice. Here's just a bigger picture of that image of the metal cations and these delocalized electrons. When we look at metallic bonding strength, it comes down to 2 familiar things: the size of the cations and the number of delocalized electrons. In other words, the number of valence electrons that that metal has to lose. So typically the smaller the ion, the stronger the bond. So these small ions are typically to the far right and close to that metalloid line. Think elements like aluminum and gallium. Aluminum and gallium would also form strong metallic bonds because they have 3 valence electrons which they have to lose and contribute to the sea of electrons. You'll see down here at the bottom that these group 1 metals have a +1 charge and these group 2 metals all have a +2 charge. We would assume that these +2 charge cations are going to have a stronger bond. Metallic bonds don't have to be just one type of metal cation. We can blend and mix metal cations together to form different types of metal alloys. Brass, for example, is copper and zinc mixed together. Bronze is copper and tin. Steel is iron, carbon, chromium, and manganese. 24-karat gold is an alloy. When you buy gold, it's not pure gold because pure gold is very soft and we need to make it more rigid so we can use it in things like jewelry. An amalgam is simply an alloy that's based on mercury. Because mercury is a liquid metal, typically amalgams have a low melting point. We used to use them in dental work before we got synthetic substances that looked a little closer to the color of a tooth. Alloys can be used for anything, and we mix metals together based on their specific properties. Even the edge of a razor blade is a specific alloy that is resistant to corrosion and stays sharp. Metallic properties often have a lot to do with that sea of electrons we talked about. Metals are malleable and ductile, meaning they can be molded and strung into thin wires. They're also conductive. In order to conduct heat and electricity, you need free electrons that have the ability to travel. If you want to send an electrical signal through a wire, it needs to have electrons that can travel through that wire. And since there is a sea of electrons that are mobile and flexible, metals are great conductors. They're also very lustrous because of those free electrons. If you shine a light on a metal, it reflects a lot of that light back. If you energize those electrons with a photon of light, it's going to give off lots of wavelengths of light. Metals have strong bonds, making them have a high melting point and a high boiling point. They also have a very high hardness level, and the stronger the bond, the harder the metal. Here's some tables showing some covalently bonded substances like methane and water and their melting points. Then we have ionically bonded substances, and their melting points are a little bit higher. But then with these metallic solids, some are low, but some of these metallic bonds are very strong and therefore have very high melting points. After this lesson, you should be able to name and calculate the percent composition of hydrates. You should also be able to understand how metallic bonds are formed between cations in a sea of electrons and some of the properties of those bonds. Good job today. We will see you next time.